Hello Year 11, I wanted to go through a paper 2 now, so obviously this is a calculator paper and I've done the AQA June 2018 paper 2, a paper version of which and a mark scheme of which are available. I will link those in for you to have a go at. I think really good practice here, as with my paper 1, walking talking mark would be to print off a paper or certainly to have it open and to be having a go at the questions as we go through. You can kind of pause it, have a little look and a go at the question yourself and then play it through and have a look at what I did, or you can just kind of play along in real time with what I'm doing if you'd like to. The first question is asking me to work out the position of the term that has a value of 0. So n always tells us the position. Whatever n is the position. So ultimately, I'm trying to figure out the value of n when this equals 0. So I'm going to put 0 equal to 1420 take 5n all divided by 1420 plus 5n. Now, if you consider that denominator as kind of a bracketed number, if you multiply that up, it's going to become 0. So actually, if you times both sides by 1420 plus 5n, you just end up with 0 equals 1420 minus 5n. So you can add 5n to both sides. That equals 1420. You can divide by 5 and you get whatever you get. I feel like I should really be able to do that in my head. There's a calculator paper, so make sure that you're relying on your calculators a little bit. Lean on them, but make sure that you're showing all of your working out through this. So n is 284, so it would be the 284th term. Next, it wants to write down the limiting value of the sequence as n. This means tends to, so as n becomes, if you like, tends to, and this is infinity. It's a sign for infinity. So basically, as n gets really, really, really big, what's going to happen to the sequence? So let's think about that. If I've got 1420 and I take away a really big number, and I've got 1420 and I'm going to add a really big number, then you're going to end up with a situation where the 1420 is kind of irrelevant because the top will end up kind of becoming minus 5 lots of a really, really big number. And the bottom will end up becoming 5 lots of a really, really big number. Now, the 1420 is kind of irrelevant, that's the starting point. So you'd end up with negative 5 over 5 because the n's would cancel. Remember that they're just really, really big values. And you'd end up with the limiting factor. As n gets really, really big, you're just going to have a massive negative number divided by a massive positive number. So it's just going to be roughly negative 1 because you're going to have negative a really big number that's very similar to the positive really big number on the top. So you just get closer and closer to negative 1. Now, in a pressure situation on a calculator, you could just start doing table function, programming in this nth term, 1420 divided by subtract 5m divided by 1420 plus 5n. You could program that in table function and make your numbers really, really big and keep going bigger and bigger and bigger and maybe take a reading every 100 or even every 1,000 and just seeing that it would get closer and closer to negative 1. Because it's only a 1 marker, you could probably get away with that, even though it is a little bit of a cheat. Okay, question 2 gives me 2 points that are on a straight line with a gradient of 12. Gradient of 12 immediately should make you think y equals 12x, but I don't know the y-intercept. So I know the equation of that straight line is y equals 12x plus something. And I also have a pair of values. I've got an x coordinate and a y coordinate, so I can substitute them into that. So I know that when y is negative 10, that is equal to 12 lots of negative 3 plus c. So now I can figure out c. Negative 10 equals negative 36 plus c. So 26 is equal to c. So the equation of the straight line is actually y equals 12x plus 26. And then they're quite kind to you because they say one possible pair of integer values. Well, that just means you can come up with anything. And I wouldn't be too smart here. I'm going to go straight up and say, okay, well, what about when x is 0? If I put a 0 in there, 12 lots of nothing, add 26, y just becomes 26. So I know for a fact that that's an integer value that works. Now, I would definitely recommend starting with your x value, subbing it in and calculating your y value from it, because then you can't really go wrong and you're always going to get integers. If you come up with a y value, there's a possibility that if you then take away 26 and divide by 12, you might not get an integer. But honestly, because they're being so kind and letting us come up with one possible pair, so any possible pair, obviously other than -3 and -10, then I'm just going to go with 0. 0 is a really simple number to substitute into things, isn't it? Now, this is a bit of a gimme, and you should be quite used to this kind of question coming up on a calculator paper. It just is a really simple bit of substitution. It's a calculator paper, so I'm going to show what I'm doing. So I'm doing negative 5.5. And remember that your calculator doesn't always deal with negatives in the way that we want it to. So if you're putting a negative in for a bit of substitution into a calculator, put some brackets around it. I actually don't think it'd matter too much for the numerator of this fraction, but I do think it'd matter here. Because if you do negative 5.5 and square it without the brackets, we know that calculators do something a little bit daft at that point, where they square first, then they make negative. So key message, if you're substituting a negative number using your calculator, put the negative in brackets, then do what you want to it. Okay, so I'm putting all that in, and my answer that I get out when I put that into my calculator is negative 14/125. It hasn't asked for it in a certain way, so I'm all right with leaving that as a fraction if I wanted to. Or if you do prefer to press the S to D button, then you get negative 0.112. And that's a very nice, easy mark to have. 3b, a little bit tougher, so I'm just going to jot the formula up here so that I don't forget it. We've got p was equal to m plus 2 all divided by m squared plus 1. And again, it's a little bit of substitution and then a bit of solving. So we know that that equals 2, m plus 2 over m squared plus 1. I'm going to multiply up by that whole bracket so that I get 2m squared plus 2 is equal to m plus 2. Then I'm going to make it equal to 0 so that I can solve it. So that'll be 2m squared minus m. And then I'm going to take off the 2, so that actually just equals 0. This factorizes quite nicely if you just pull the factor of m out. So it's m brackets 2m minus 1 equals 0. And that gives you your two values of m. So m could equal 0, because remember you're looking for ways of expanding that bracket and getting an answer of 0. Well, if m was 0, that would work. Or if this whole bracket was worth 0, so if you like 2m minus 1 could be the bit that's worth 0, so 2m would be worth 1, so m would be worth a half. So our values that work are 0 and 1/2. Here, straight away, we should be thinking about circle theorems. So, one of the circle theorems is that if you make an angle at the centre, it's twice the angle on the circumference. So I think straight away that W is worth 2 lots of X. So I'm already kind of ruling out this one. I don't think that's right. And I don't think that's right because they've got the X relationship slightly wrong. It's W that you would find out by doubling x, not the other way around. So it's got to be one of these two. Now, x add y equaling 180 is a bit of a strange one. If you think here, this needs to be 180 take away y, because you've got angles on a straight line. But also, if you ignore this for a minute, this line, you've got a cyclic quadrilateral. So actually, that would also be 180 take away x. Well, if you take away y from 180 and you get that angle, and you also take x from 180 and you get that angle, then I think we can assume that x and y are equal to each other. They don't add up to 180, because when we subtract them from 180, either one of them, we get the same answer. So therefore, they must be equal to one another. This is a little bit of a strange question because it's just about a combination of different functions. If you're all right plotting graphs and you can plot them, and you just need to take note of like the range of which function is existing for which values of x. So first of all, from -4 to 0, the function of x is just x plus 4. So if x was -4, add 4 on just gets you to 0. So that would be there. And then -3 add 4 is 1. -2 add 4 is 2. -1 add 4 is 3. And I'm going all the way up to 0. So when x is 0, then the y would just be 4. Then after that, it wants to be 4 minus 3x, which means the y-intercept would be 4, and the gradient would be -3. So 1 along and 3 down. So I think it'd end up there, and then 1 along and 3 down. And then I've got to the end of that range as well, because I've got to 2. So I've gone from -4 to 0, I've gone from 0 to 2. Now between 2 and 5, it just wants it to be -2. So that's just going to be a straight line from that point. Now, I'm not going to be brilliant at drawing these as straight lines because of the equipment that I'm using, but you should join this up with a straight line and ruler. So it'd be a straight line going up there, then a straight line with a gradient of 3, a straight line, so not like the one I've just drawn, and then a nice straight line all the way up to 5, but not going past 5 because obviously it's saying equal to or less than 5. So you don't need to carry it on, and you don't need to go back past -4 either. And that's that. So it's just thinking about these ranges. You know how to plot all of the graphs that are the 3 different functions of x, and it's just about thinking about the ranges of x. Okay, next up, these questions are question 6, I think both parts, are possibly quite similar. So here it wants me to work out the range of f of x. So I need to look at this and think about, are there any numbers that this can't possibly be? Or when we've got a squared, we know that x squared is always going to be, no matter what number I put in, it's always going to be greater or equal to 0, right? So if that's true, then f of x is always going to equal at least, so it's going to be greater than or equal to 0 take 7. So f of x as an inequality can't have a value that is any less than -7. In fact, the only way it can have that value is when x is 0. As soon as x takes a value either greater than or less than 0, squaring it makes it positive, and then we're taking away 7 from a positive number, so we're going to have just slightly less than -7 at least. I hope that makes sense. And then this part of 6, I think there's a little bit more to do, but I think conceptually is a little bit easier. So I'm just going to rewrite out that g of x is written as 1 take away 3x. But it also has a range of x. So it says that that's for x values that are greater than or equal to -4 and less than or equal to 4. So ultimately, it just wants you to figure out the range of values that g can take. So let's use the minimum value of x, that is -4. So g of -4 would be equal to 1 take away 3 lots of -4. And that's 1 take away -12, which is 13. Then if we work out g of +4, it's going to be 1 take away 3 lots. +4, which is 1 take 12, which is -11. So we know that g of x is always going to be somewhere in between, and we can put the equal to sign as well because it's allowed to equal these values somewhere in between -11 and 13, and that's quite a straightforward one as well. This question says solve 2 lots of f of x equal to g of x. You must show you're working out. Give your answer to 3 decimal places. Now I think that's a bit of a clue of how we're going to solve this, but I'll come back to that in a second. So first of all, it says that when we double the function of x, so we have 2 lots of x squared minus 7, we get g of x, which is 1 minus 3x. So expand that bracket, you get 2x squared minus 14 equals 1 minus 3x. Then you're going to make it equal to 0 so that you can solve it as a quadratic. So 2x squared plus 3x. And then what's it going to be? Minus 15 is equal to 0. Obviously, we could think about 3 and 5 and factorising, but with a 3 and a 5 where you double one of them, I'm not sure it's going to work, because 3 times 5 is 15, and then you can either have 6 and 5 or 10 and 3, neither of which I think work to give you 3x. So therefore I think we're going to have to use the quadratic formula, which obviously you just need to know what a, b and c are to use it. So we're going to say it's minus b, so minus 3, plus or minus the square root of b squared, which is 3 squared, minus 4 times a, which is 2, times c, which is negative 15. That's quite useful, the fact that that's a negative, because it means that minus 4ac is actually going to be a positive, so we're going to square root something that's positive, which is good, because if you try and square root a negative, you sometimes, well, you always end up in trouble. So all of that is going to be divided by 2a, which is 4. Here, I like to work out a little bit at a time, really. So I'm going to say it's minus 3 plus or minus, and then if you work out the bit in your square root, so you've got 3 squared, which is 9, and then you've got minus 4 times 2 times minus 15, which is 129. So you've got the square root of 129. And that's all divided by 4. And then at that point, it's quite easy because you can just type it in separately to your calculator. You can do minus 3 plus square root 129 over 4. And you can do minus 3 minus square root of 129 over 4. And get you 2 answers. It wants it to 3 decimal places. So let's just quickly do it on the calculator. For this one, I get 2.089. And then for the other one, what do we get? Minus 3.589. And there we go. There are 2 answers to 3 decimal places. Okay, this question here is a question about the area of a trapezium. So however you know the area of a trapezium, you might know it as half the sum of the opposite sides times the space between them. So that would be a plus b over 2 times h, where a and b are the parallel sides, or you may well have it as half h times a plus b. Now, that a is not to be confused with the a in this question, so your further mathematicians, I'm pretty sure you can deal with that. So that's just the general form where a and b are the parallel sides. Let's look at what we've got in this trapezium here then. Well, on the top, between S and R, along the x-axis, the movement is 4 because it goes from 5 up to 9. And on the bottom, between P and Q, the movement directly horizontally is 8. So we know the parallel sides, but we don't know the height. In fact, the height is how far up the y-axis we've gone, and the y-coordinate, as you can see, is a in each case. So I think we're dealing with a height of a. That's a little bit confusing if you know the formula is a plus b, but don't worry about it. What that means is we would do 4 add 8, and we would half that. Then we would multiply by the height, and the height in this case is a, and we get an answer of 63. So 4 add 8 is 12, half of that is 6, so we know that 6a is 63. Really simply, we can divide 63 by 6, and it's 10.5, isn't it, or 10.5. Here's a sketch of triangle ABC. Point P is on AB, and A to P to B is 3 to 1, which ultimately means that this bit of the line is 3/4 of the line, and this bit of the line is 1/4 of the line. Once we know that, it becomes a little bit easier to do what we need to do. We want to work out the length of P to C. The reason I'm interested in this line AB first, though, is because I think we can figure out the coordinates of P. I'm going to draw some perpendicular lines here and think about the distances between A and B. Up the x-axis, it goes from 1 to 7, so the horizontal movement is 6. Up the y-axis, it goes from 1 to 6, so this movement is 5. So if I want to go 1/4 of that and just go from P to B, I can quarter both of those measurements. So 1/4 of 5 is 1.25, and 1/4 of 6 is 1.5. So I think the coordinates of P are actually, well, they're 1.5 back from 7, so they're 5.5. And the y coordinate is 1.25 up from 1, so that would be 2.25. Now this is going to become a Pythagoras question, because I'm going to try and go from P along to C. So I'm going to use some Pythagoras here, draw again my perpendicular lines so that I can figure out the distance of this line, the hypotenuse there. So as you can see, you've got a little right angle triangle here. Sorry, I'm not very good at drawing straight lines on this. That's why I've done them as dotted lines, but I guess straight lines would make a little bit more sense. So from P to C, the x-coordinate of P is 5.5, the x-coordinate of C is 9, so that's gone up by 3.5, I think. We've done that right? Yeah, 0.5 to 6, and then add 3 to 9. Great. And then the y-coordinate has gone from 2.25 up to 12, so I think that's gone up by 9.75. That means that to get from P to C, it would be, to do some Pythagoras, the square root of 3.5 squared plus 9.75 squared. So 3.5 squared, add 9.75 squared. Put that into your calculator as one swift go. Let's have a look at what we get. 3.5 squared, add 9.75 squared, all square rooted. How accurate do you want it? 4 significant figures, that's 10.36. So 10.36. Right, here we've got an expression for y, which is 2x to the power of 7 plus 15x squared divided by 3x. We want to work out the value of x when dy by dx, so the differentiated expression, is equal to 133. So the first thing I'm going to do is rewrite this actually. I'm going to have this as 2x to the 7 plus 15x squared. I'm still going to divide it by 3, but I'm going to bring the x up. So I'm going to say that that's all multiplied by x to the minus 1. Because I can't differentiate in the original form. It's going to be too complicated. I need just individual terms with powers of x. So let's have a look at what that leaves us with. That would leave me with x to the power of 7 times x to the negative 1 is x to the power of 6. So you've got 2/3 of x to the power of 6, and we've got 15/3, or 5 if you like, x to the power of 1. So we'll just tidy that up again, sorry. 2/3 x to the power of 6 plus 5 x. And we don't really write to the power of 1. Now I can differentiate that. So remember that when we're differentiating, we're going to multiply down by the power and then take 1 off. Okay, so I don't know what's happened there with my writing. Dy by dx is equal to, well, 6 times 2/3 would be 12/3, which is 4x to the power of, take 1 off, 5. And then that's just going to be plus 5. Because you times down by the power, which is 1, so 1 times 5. Then you take 1 off the power, so that becomes x to the power of 0, so you haven't got any x's there. Next up, we're going to put that equal to 133, because I want the value of x for that. So 4x to the power of 5 plus 5 is equal to 133. Let's take the 5 off, gives us 128 equals 4x to the power of 5. Going to divide by 4 next, so that's 6432, isn't it? So 32 is equal to x to the power of 5. And then you should know that the fifth root of 32 is 2, because 2, 4, 8, 16, and then 32. So my value of x is just the, we should show how we've got there, the fifth root of 32 is equal to x. So right here we've got a transformation matrix that maps a point 1, -3 onto a point 1, 4. So this is just asking you for your understanding of multiplication of matrices. So ultimately we've got A, B, 2A, 3B, and that's being multiplied by 1 and -3 to end up at 1 and 4. So we need to remember the rule of multiplying is that we multiply the rows by the columns. So if I multiply that first row, I'm going to do A times 1, and I'm going to add to that -3B, and that ends up mapping to the point 1. And then I've got, if I multiply the second row by the column again, so I've got 2A times 1, add 3B times -3, and that equals 4. Just going to tidy those up a little bit. So I've actually got A, take 3B, is equal to 1. I've got 2A, take 9B, is equal to 4. And I need to do something with those. So I could triple the top one, or I could double the top one. Either way, it would work. So if I double that top one, then I'll bring it down the bottom. I've got 2A minus 6B is equal to 2. So all I've done is times that whole thing by 2. And Probably ignore that one for a little bit now, because then if I subtract them, that's going to get rid of my 2a's, and it's going to leave me with -9 minus -6 is -3b. And 4 take away 2 is 2, so b is equal to -2/3. Then you just need to substitute back in and get a. So that top one then becomes quite nice, doesn't it? Because you've got a, take 3 lots of -2/3 is equal to 1. So that's a. Take add 6/3, which is add 2 equals 1. So take off the 2 and you get a. Oh, a bit of a gimme question here, which is nice. Expand the bracket. You should probably be able to expand the 2 brackets first and just write that that's x squared plus 5x plus 6. Then that all just needs multiplying by x, add 4. So you get x cubed plus 5x squared plus 6x plus 4x squared plus 20x plus 24. It's just a matter of neatening it up a little bit. So you got 1x cubed, we got 9x squareds, we got 26x plus 24. Next, it wants us to write this as a single fraction in its simplest form. So, yeah, the common denominator here is a bit of an interesting one, isn't it? But let's go with, we could multiply the one on the left by, or the first fraction, by x, couldn't we? If we multiply top and bottom by x, we get 7x over 9x squared. And then we multiply the other one by 3, we would get 6 over 9x squared. Add them together, you get 7x plus 6 all over 9x squared. Well, this one's a bit more fun because we've got to multiply through. I think just do it bit by bit. So if I multiply across on the top first, we're going to get x 4 multiplied by x plus 2 all divided by x brackets x plus 4. Let's just multiply in the first one, and then I'm going to keep that the same. I'm going to swap that for a multiplication, and I'm going to flip the last fraction so it looks like this. Now, I think there are going to be a few things that simplify here, and I might even rewrite that second fraction. So I've just noticed that it does, you can factorise the numerator now, can't you? So I might just rewrite that as 3 lots of x plus 4 all divided by x squared, because now you can see that an x plus 4 will cancel on the top and the bottom, so I'm not even going to bother multiplying those. Also, I think we can cancel out 2 of those x's if we get rid of that, and then even cancel out that squared x with that x there to leave me with just a 1 on the bottom, and it would have x to the power of 1 x plus 2, and that's just the same as, what form does it want it in? Ax squared plus bx. So that's just the same as 1x squared plus 2x, because all of it cancels. So the key was all in this factorisation, and then obviously cancelling through a few of these x's over here as well, and realising that you can cancel 2 off with the denominator during that division, or that keep swap flip multiplication. Cancel 2 of them off there, cancel 1 of them off the bottom as well, and that's what it simplifies to be. So x squared plus 2x. This question is really just getting you to understand and read what's going on. So we've got the graph of tan x. This shouldn't be an unfamiliar shape to you. It's got what we call, these are called asymptotes here, where it never actually reaches 90. The reason for that, if you think about your right angle triangles, is tan is opposite over adjacent, where you can never have an angle of 90 degrees with an opposite over an adjacent, because if you've got an angle of 90 degrees, then your opposite is actually your hypotenuse. So that's why it can never quite reach the 90. But you shouldn't be unfamiliar with the kind of the repetition of this and the symmetry of it as well. So it's asking us how many solutions of tan x equals k, where k is greater than 0, are there between 90 and 360. So actually for this question, it's only between 90 and 360, so you can kind of wipe that out. We're only talking about from here to here. And it also tells us that k is greater than 0, so k has got to be above the x-axis. Therefore, there's only going to be one solution, because it's going to lie on this bit here. This is the only part of positivity on that graph. If it was less than 0, then it might hit twice, because, for example, if it was there, then the same solution would also read off there. But because it's positive and it's greater than 0 and it's between 90 and 360, there's only going to be one solution there. This one's a bit trickier still conceptually, because it's talking about how many solutions of sin x p minus 1 are there between 0 degrees and 180 degrees. It's also interesting to note this, that p is between 0 and 1, so it's a positive number that's between 0 and 1. You may sketch a graph to help you, so I'm just going to quickly sketch the graph of sine of x. So this is x and this is y. I'm just going to quickly draw y equals sine of x. And I'm drawing it from 0, let's have 90, 180, 270, 360 roughly, so 90, 180, 270, 360. Now, sine of x, I always think is an S. So it starts off positive, stays positive, then it goes negative down here. And it tops out at 1 and bottoms out at minus 1. So we're talking about how many solutions there are for sine of x of p take away 1. Well, if you think that p is between 0 and 1, if you take away 1, it's got to be negative. Because if you're taking away 1 from something that is in between 1, let's just wonder if we can show it algebraically here. So if I take away 1 from that, so if I go p take 1, that means that would have to be between, I don't know what happened with that there, but I can't really undo that actually, negative 1 and 0. So you're effectively talking about a negative value, and it's only interested in between 0 and 180. Well, how many negative values are there between 0 and 180? There aren't any. There'd be some in this section after 180, but in between 0 and 180, there are going to be 0 solutions to that. And here they're really pushing you to kind of have an understanding of all of your trigonometric graphs. So again, I'm going to draw this time y equals cos of x, just to try and help us answer this one. So once the coordinates of each point where the graph crosses or meets or intersects an x-axis. So cos is a little bit different to sin. If we call that 90, 180, 270, 360. Cos is kind of the sine graph but dragged back 1. So it starts off positive. Sorry, I don't know what happened there. Starts off positive, then comes negative, turns back through, goes positive again. And it'd be positive into between 360 and 540 or whatever comes next. And that, again, it tops out at 1 and negative 1. So where is it hitting the x-axis between 0 and 360? Well, it's hitting it at 0 No, it's not hitting it at 0, sorry. It's hitting it at... Oh, sorry, meets an axis. So not an x-axis. So yeah, it would be. It hits it here, it hits it here, and it hits it here. So we just want to state the full coordinates of all of those. So it hits at 0, 1. It hits at 90, 0. And it also hits at 270, 0. Factorise fully is, this is quite nice for question 14, I would suggest. So let's look at the coefficients first. I think they're all divisible by 6, which is the highest common factor there. That'll leave me with 2, a 3, and a 4, and that's quite reassuring because they don't have any common factors between them. Let's look at the unknowns now, the variables. They've all got at least one p, so p can come out, and let's kind of keep tabs on that. We've got the p on the outside, so we don't need that. They've all got at least 2 q's actually, so I'm going to have 2 q's on the outside. That gets rid of all of that, it gets rid of all of that, and it takes that down to just 1. And they've all got an r, at least one r. So that would get rid of that r, get rid of that r, and it would eliminate the need for the r squared there. So then what are we left with? Well, next to the 12, which I've divided by 6 to give 2, I've just got 1q, and then it's a negative in between, and remaining there, I've just got 1r. And then at the end here, well, because I've got p q squared r on the outside, I think that just becomes plus 4. You could always double check this by expanding back out and double checking that you've got everything covered, but I'm pretty happy with that it is 6p q squared r times 2q minus 3r plus 4. All done. Lovely. I do really appreciate this question. It's asking us to factorise fully now. It's a little bit more complicated, giving you an answer in its simplest form. I like this little warning here. Do not attempt to expand these. And you'd be right to kind of listen to that, because you'd be here for a really long time. You certainly would be wanting more than 3 marks for that. So here, if you think about it, let's just look at the coefficients. Let's pretend that these are, I don't know, we could even do a bit of substitution here and say, right, I'm going to just bring in another unknown and say that u is equivalent to y plus 3, because that seems to be cropping up quite a lot in that expression. So then effectively, using that substitution, I've got 6u to the power of 5 plus 4, and again it's y plus 3, so I can say 4u to the power of 4. If I wanted to factorise that, then I'd be looking at the coefficients. Well, they could both be divided by 2, so I'll have a factor of 2 on the outside. And then if you think about it, the highest value of u that they both contain is u to the power of 4. That would then leave me with 3u plus 2. Only thing is that u never really existed. So actually what I've got is 2 lots of y plus 3, if I substitute back in now, to the power of 4, multiplied by 3 lots of y plus 3 plus 2. And I should really expand that and simplify that second bracket as well. So we'd have 2 brackets, y plus 3 to the power of 4, multiplied by, and that would be 3y plus 9 plus 2, close brackets, which can be simplified just one more step, y plus 3 to the power of 4, brackets 3y plus 11. And at this point, we should just double check that I can't factorise the second bracket, but I can't because there's no common factor of 3 or 11, so I'm pretty happy with that one. And we go again with a little bit more factorising. Now, on the face of it, this just looks like I should think about a common factor of both of these, and I certainly should to start with. I think they can both be divided by 3. They both got a factor of 3 for sure. So 48 is 3 lots of 16. and 75 is 3 lots of 25, and I've still got the x squared in there. But then that starts to look like something a little bit different. If you think about the old x squared minus another, like a squared number, it's called the difference of two squares. So it would have looked a little bit like, I don't know, x squared minus 36, let's say. You can factorize that into x plus n and x minus n, or in a slightly simpler example, x plus 6 and x minus 6, because you don't get any x to the power of 1s in the middle, as you get positive 6x and negative 6x, they cancel each other out. I think we've got something similar going on here, because we've got 4 minus 5x, because we've got two square numbers there, and that would be multiplied by 4 plus 5x, because again you'd get 20x minus 20x, so you wouldn't get any x's, but you would get 4 times 4, and you would get minus 5 times 5, which is 25x squared. So I think that is it fully factorized. So we'll whack the 3 down. We've got 4 minus 5x multiplied by 4 plus 5x. Again, the more of these questions you do, and the more you look up practice questions from, this is the official title is AQA Level 2 Further Mathematics GCSE. The more you see, work out the rate of change. Well, the rate of change of something with respect to it, it's just differentiating. So here, it effectively wants us to find dy by dx, because that's how fast is y changing with respect to x. The thing we need to do first, though, is expand that bracket out. So x squared times x squared is x to the power of 4 minus 9x squared. The reason we need to do that is because now we can just follow our simple rule of multiplying down by a power and taking one off. So that would become 4x to the power of 3, and that would become minus, well, 2 times 9 is 18, x to the power of 1. You don't really need to write the 1. And it wants to know the rate of change when x is equal to negative 2, so we need to figure that out. So we want to do 4 lots of negative 2 all cubed minus 18 lots of negative 2. Remember, this is a calculator exam, but here you've got to be really careful when substituting in a negative, because your calculator isn't very, it's the one big downfall of calculators. They're not very good at subbing in negative numbers. If you're doing it, make sure you put brackets around the negative all the way through this. So this would be 4 lots of, well, minus 2 times minus 2 is positive 4, but times that by negative 2 you get negative 8. So it's 4 times by negative 8. And actually, I think we're going to end up adding 36, because negative 18 times negative 2 is positive 36. So that would be negative 32, add 36, becomes 4. So the answer to that one is 4. Right, here it's given me 3 different expressions for A, B, and C, and it's suggesting that 2 lots of the A plus 3 lots of the B all squared is equivalent to A plus B plus C. So I'm going to kind of work on the left-hand side and the right-hand side and try and show that they are equivalent. So for the first part, on the left-hand side, I'm going to do 2A and I add 3B. And then I'm going to square it. I'm just going to figure out what that looks like. So 2 lots of the A would be 4 minus 10x, because I've just doubled both of those things. Let's triple all of the stuff on the B. So we're going to be adding 9x minus 3. And I'm going to square that in a minute once I've neatened it up a little bit. So what do I actually end up with? Well, I've got 4 take away 3, so that's 1. I've got negative 10x plus 9x, so that's just a negative x. So I need to square that. That would give me 1 squared is 1. It would give me minus x and minus x, so negative 2x. Negative x times negative x is just a positive x squared. So I think that is what 2a plus 3b all squared is. Now I'm going to over here try and figure out what a plus b plus c would actually look like, and then hopefully prove that identity. So I've got 2 take 5x. I'm adding to that 3x and negative 1, and I'm also adding to that an x squared. So what do I end up with? Well, I've got, I might just do this bit by bit just to make sure that I'm fully getting the full mark. So I've got 2 minus 5x plus 3x is actually negative 2x. Still need to take off 1, still need to add x squared. So that ends up being, I can do the 2 take away the 1 next. So 2 take away 1 is 1, take away 2x plus x squared. So therefore 2a plus 3b all squared is always going to be equivalent to a add b add c for all values of x. Next up, circle has the equation of x squared plus y squared equals 29. P is the point negative 5, 2. Show that P lies on the circle. Well, it's just a little simple bit of substitution. So first off, you just need to put a negative 5 in, give it a square, and then you're going to add 2 squared to it, and you're ultimately looking to see if the answer to that is 29. Well, 5 squared is 25. You're going to add 2 squared, which is 4, and that gives you 29. So it is on the circle. Right here, the tangent to the circle at P intersects the x-axis at Q. I just got to remind myself of the point P because it's on the previous slide, obviously. So point P is negative 5 and 2. Intersects the x-axis at point Q. So because it's just x squared add y squared, we know that the centre is 0, 0. So it looks a little bit like this. We know that the radius is the root of 29. We know that at negative 5, 2, that's point P. Just jot that on, negative 5 and 2. And we're thinking about the tangent here hitting the x-axis at Q. And we're looking for the x coordinate of Q. We know that the y coordinate is 0, by the way, because it's hitting the x-axis, so we already know that that's going to be 0. So here it's all about gradient, because we know that the gradient of the radius there, well, it's going, what is it doing? It's going 5 across and 2 down. So the gradient of the radius at P is equal to, it's going 5 across and 2 down, so it's negative 2 over 5, which means the gradient of the tangent, because they meet at right angles, they're perpendicular, would be 5 over 2. So it's the negative reciprocal. Well, because that gradient was already negative, this gradient's going to be positive, and the reciprocal is the flip of the fraction, remember. So now we know that the equation of that tangent is y equals 5 over 2x plus something that we don't know, we'll call it plus c, but we do know that P's coordinates lie on that. So we know that when y is 2, x is equal to negative 5, so we can figure out c. So we know that 2 is equal to negative 25 over 2 plus c. We can add the 25 over 2, so that would be 29 over 2, I think, is equal to c. So now we know that the actual equation of that tangent is y equals 5 over 2x plus 29 over 2. Next, we're going to substitute Q in. So we want to know the point where this hits the x-axis, so we're going to whack y is equal to 0 in. So y is equal to, just notice that we can call this 5x plus 29 all divided by 2. Times up by 2, you get 0 still is equal to 5x plus 29. So if you take the 29 over and then divide by 5, you get x is equal to negative 29 over 5, which is a very, very unusual answer, but I guess on a non-calculator paper that's okay. On a calculator paper that's okay. And you could express it as a decimal if you wanted to, which is negative 5.8. Now it wants us to work out all the integer values of x. This feels like a massive departure from that last question. All of the integer values for x, for which 4x plus 3 is greater than negative 5, but less than or equal to 13. So first off, let's take away 3 from all of it. So that would be negative 8. Keep the inequality signs the same. We're just left with 4x in there, and that becomes 10. Then we're going to divide by 4. So everything over 4. It's going to be x less than or equal to 10 over 4 or 5 over 2, or if you like, we could just write 2.5 because we're going to deal with integer values, and then here that will be negative 2. So it's all of the integer values that are greater than negative 2. So the first one's going to be negative 1, 0, 1, 2. It can't be 3. It's allowed to equal 2.5, but it can't actually be 3. So I think that's where we're going to stop. It's just negative 1, 0, 1, and 2. Work out the range of values of x which x squared minus 11x plus 28 are greater than or equal to 0. So first thing I'm going to do, I'm going to see a quadratic. Should always look to try and factorize it because it will usually tell me something else. So what have I got there? It's 4 times 7, isn't it? So I think if they were both negative, they'd give us negative 11x, but also they multiply together to give 28. Now the next thing when we're solving inequalities I like to do is actually plot y equals the expression of x. Now if you think about solving this, the roots would actually be x is 4 and x is 7. So they'd both be positive, 4 and 7. And the graph, it go through plus 28 on the y-axis as well, but that's a bit irrelevant. Excuse my rubbish parabola, I'm not very good with this tablet thing, but that's roughly how the graph would look, right? And it wants to know when that is greater than 0. So we're actually interested in not when it's below 0, but when it's greater than 0. So anything here and anything here. In both of those cases, that expression is greater than 0. So actually, we're interested in x being less than 4, but also when x is greater than 7. So they're just slightly subtly different, but they're our final answers. And I always think you should draw or sketch your quadratic when you're solving a quadratic inequality. So x has to be less than 4, or it can be greater than 7. In both of those cases, the whole expression is greater than 0. In between those are the bits where it is less than 0. So if the inequality was the other way round, we'd be able to write it as just one inequality with x lying in between 4 and 7, but actually we're interested in when it was greater than 0. Right, this question is really quite tough. I'm going to run a session after the holidays before your papers start on transformation matrices, but I'll try and do my best to kind of give you a little bit of an idea of what they look like. So first off, we want to do matrix multiplication to show that in the xy plane, a reflection in the line y equals negative x, followed by, I'm going to deal with each of these transformations one by one actually, and I'm going to express them as matrices. So I'm going to call this first one A. And I just want to quickly think about what that looks like. Now, if you consider having a point, and I've picked one at random of the coordinate with the point, the point with the coordinates 2, 5. If I reflected it in the line y is negative x, it would end up down here, wouldn't it? And it would end up being -2, -5, because that's where that reflection would occur. So what I need to do is consider a matrix that when I multiply 2, 5 by it, it maps and gives us the result, very similarly to question 10 on this paper earlier on, -2 and -5. If you remember that you multiply the rows by the columns, I'm going to do something times by 2 and something times by 5. Well, I actually don't want the 5 to end up on the top. I just want to end up with an answer of -2. So I want to multiply the 2 by a -1. I want to multiply the 5 by a 0. And then if I consider what I want to get on the bottom, I need a -5. So again, I want to multiply something by 2 and something by 5 and end up with just a -5. So I don't want the 2, but I want to multiply by -1 because that will map the 5 onto being -5 there. Just to show you how that would work if I did multiply those matrices out, I would do -1 times 2, add 0 times 5. And I'd end up with 0 times 2, add -1 times 5. And so if you sort that out and add them, you end up with this. So the matrix that represents a reflection in the line of y equals -x can be expressed as -1, 0, 0, -1. Next up, I can consider my same coordinate of 2, 5, a rotation 90 degrees anticlockwise about the origin. So that point would end up over here, the coordinates of which would just be, the y coordinate would stay the same, but the 2 would become negative, the x coordinate would become negative, and the y coordinate would be 5. So if I try and do a similar calculation over here, again, I want a matrix that multiplies 2, 5, but this time gives me an answer of -2, so it changes the x, but it keeps the 5 the same. So it's not going to be too dissimilar to that one that we've just seen on the top. In fact, the top line is going to be the same, isn't it? Because it will give me -2. So I want a -1 and a 0 because I don't want that 5. But I want the 5 on the bottom for the y coordinate to stay the same. So I'm going to multiply that. Well, I don't want the 2, so I'll multiply that by 0. I do want the 5, and I don't want to change its positive or negativity, so I'm just going to call that 1, and that would multiply that point to map it onto -2, 5 instead. So I'm going to call that, sorry, I forgot to note up my first matrix, which is A. I'm going to call this matrix B here for transformation B, that rotation. Next, a reflection in the x-axis. So again, I'll return to my axes up here and think about what would happen to the point 2, 5, which is just a completely random coordinate, by the way. I've been trying to get my head around these matrices with a pen and paper for a minute, so I just chose a random couple of numbers that I knew wouldn't be too difficult to multiply with. But if I reflected that in the x-axis, it would end up down here. So the x-coordinate would stay the same at 2, but the y value would become -5. So again, it's not going to be massively different from the one above it. I need to multiply it by a matrix. I need to multiply 2, 5 again because that's my start point. This time, I want to end up with the 2 staying the same, but the -5, the positive 5 turning into a -5. So this time, I'm going to have 1 times 2 and 0 times 5 to give me my top number of 2, 0 times 2 and -1 times 5 to give me -5 on the bottom. And that's my matrix C. Now what this is asking for is if I do all three of these in turn, it's actually equivalent to the identity matrix. Remember that your identity matrix is a matrix that reads 1, 0, 0, 1. And it's a matrix that kind of maintains a point. It just keeps it in the same position. So here, I want to do A followed by B followed by C. So actually, just like in functions, you kind of work out backwards. So I start off with my matrix of B multiplying against A. So I'm going to multiply B, which is negative 1, 0, 0, and 1. We'll just note that up as B. I'm going to multiply that by A, because that's my start point. So negative 1, 0, 0, and negative 1. If I multiply that out, let's have a look at what we get. So remember, rows by columns. So you'd get negative 1 times negative 1. Negative 1 by negative 1 in here. Add 0 times 0. And then negative 1 times 0. Add 0 times negative 1. And then I'm doing the bottom row of B multiplied by the columns of A, so it'll be 0 times negative 1 and 1 times 0. I didn't quite leave my brackets big enough. And then 0 times 0 and 1 times negative 1. So the result of that, to neaten it up, because I still need to multiply that by C, would be, well, negative 1 times negative 1 is 1, because I'm adding 0 times 0. That, well, because you're multiplying both things by 0, it's just going to become that. You're multiplying both things by 0 down there, and then 0 times 0 is nothing, and you're adding, I forgot to put the add sign in, negative 1. So that's the result of multiplying A by B. Next up, I need to multiply C by that. So C is over here, look, just put a little asterisk next to that to remind you. So that's 1, 0, 0, negative 1. And I'm multiplying that by 1, 0, 0, negative 1. And hopefully we're going to end up with, I'll put another little asterisk up next to where the 5 marks is, we're going to end up with this identity matrix. And if we do, then we're really happy, because this is me doing C times BA. So slightly bigger brackets this time, hopefully we won't run out of space. 1 times 1, add 0 times 0. And then the second column, so the top row by the second column, still 1 times 0 and 0 times negative 1. Then we're on to the bottom row by the first column, which is 0 times 1 and negative 1 times 0. And then the bottom row by the second column is 0 times 0 and negative 1 times negative 1. I've missed the add off again there. So overall, I do think that gives us 1 times 1 is 1. Both of these things are being multiplied by 0 in the top right, so that's just going to end up with 0. Both of the things on the bottom left have a factor of 0, so they're going to end up with 0. And then negative 1 times negative 1 is 1. So we've got the identity matrix, which is just great news. Thank you for that 9-minute journey. Next question. Okay, quite a lot of information that I think is all represented on the diagram, but let's just double check first. So it's a triangular prism. I can see that. That's nice. PQRS is a rectangle. So PQRS, that's the bottom face, isn't it? That's the bit that's touching the kind of the floor that it's sat on. And angle QRU is a right angle. So it's kind of telling me that that bit there is a right angle, which isn't on the diagram, so I'm just going to plonk it on. PQ is 10, yeah, great, I've got that. QR is 12, great, I've got that. And UR is 7, that's all marked on. M is the midpoint. It wants to calculate the angle between UM and the plane PQRS. So just to give you some idea, and again, I hope that my straight lines kind of work here, we're interested in a right angle triangle that has UM as the hypotenuse. It wants the angle between UM and the plane PQRS. So that can be any part of that bottom face. But the most obvious or the workable part of that is if we make a right angle triangle that looks like that. So it's kind of cutting through the shape there. Because then if we figure out this angle here, I'll mark it as theta. That's the angle that we're actually interested in. I think once you realise that, the maths involved isn't too difficult, but it's actually thinking that that is the angle between UM and the plane PQRS. So what do I need to know? Well, I think MR would be really useful to know, because then we could do some trigonometry to figure out theta. So MR is the hypotenuse of a right angle triangle that has 5 centimetres and 12 centimetres involved in it. So I might just draw that out down here just to show you what I'm doing here. It'd be really useful to figure out MR. I don't know why I can't draw an R there. It's really not letting me draw an R. Let me just try one last time. There we go. So that's 5. That's 12. So we can quickly figure out MR by doing 5 squared add 12 squared. And I think that's a Pythagorean triple. So I'll square root that and get 13. Sorry, I should have remembered that that's a Pythagorean triple. So I know that's 13 now. And then I've got the angle in the middle, I've got the opposite, and I've got the adjacent. So it's just a matter of doing tan to the -1 of opposite over adjacent and seeing what I get. So shift tan of 7 divided by 13 is 28. Right, from the we need some information from the previous question here, because it's the same triangular prism, but this time it wants us to calculate the angle between the planes UMR and UQR. So UMR, I'm not very good at drawing straight lines, so excuse the dotted, but that's UMR. And if you remember in the last, or the first part of this question, realised if that was 5 and that's 12, then this hypotenuse down there is 13, so I'll just jot that on there again. That's UMR, and then the plane UQR is kind of, it's this face here, this side face of the triangular prism. So really we're looking to figure out this angle just here. Hold on, there we go. This angle just here, kind of R, if you like, that I've just enclosed. So you're looking for an angle. You've got 3 of the sides of a triangle, so you could quite easily use cosine rule. Now, cosine rule for, well, normally is A squared equals B squared plus C squared minus 2BC cos A. If you rearrange that for the angle, you get cos A is equal to B squared add C squared minus A squared all over 2BC. So if we substitute in our 12, 13 and 5 there, where 5 is A, and that's the most important one because it's the one that you're subtracting once it's been squared. The other two, it doesn't really matter which way around you do, the 12 and the 13. But if you call A 5, then you end up getting cos of A. Well, let's show where we substitute the numbers in first. So cos of A is equal to, again, it doesn't really matter, let's do 12 for B and 13 for C, minus 5 squared, all over 2 times 12 times 13. I think you end up with cos A, let me just have a little look, being 12 thirteenths. As a simplified fraction, obviously you lean on your calculator a little bit here and do just kind of accept what it says. So it's simplified that fraction for me, I'm happy with that. And then to figure out the angle of A, I'm just going to do cos to the minus 1 of, you could keep the answer in and just use A and S, of 12 over 13. You do that, you should get, as long as your calculator's in degrees mode, 22.6. If you get anything other than that, then just check that you're still in degrees. Okay, this question we are talking about a continuous curve of y equals f of x has exactly 2 stationary points. That basically means it's got 2 points where the gradient is 0, because it's that's what stationary point means, basically where the rate of change is equal to 0. Here is some information about the curve. So it tells us that when x is less than -1, then the rate of change is positive. That means that the gradient is effectively positive at this point. So if you like, it's kind of the line must be going up because the gradient is positive. Then at -1, it flattens off. So then it kind of flattens off here. And if it's gone there and then after -1 it goes negative, we kind of know that it's gone through this sort of movement. So it was positive because there the gradient will be positive, and then afterwards it's gone back down negative, and then here it's -1. When x is -1, the rate of change is kind of 0, so it's a stationary point. That means that that must be a maximum. So where x is -1 has to be a maximum point because it's topped out, it's gone positive, it's flattened out, and then it's gone negative. So it must have reached a maximum point. Now this bit here actually tells me that when I substitute -1 into the function, I get 3 out. So that's into the original function up here, I get 3 out. So it tells me that the y value for that point is 3. So that's a maximum. It's enough to say max actually, but we should really look to struggle all the way to the end of the word. So we're going to call that a maximum point. Next up is a little bit different, right? Because here the gradient is negative, and then it says when it gets to 2, it goes to 0 again. So it obviously flattens off. So I kind of dealt with that. But then weirdly, afterwards, it goes negative again. So it's not as easy as saying that this is a minimum, that when x equals 2, it's a minimum. Actually, it's a point where the gradient just kind of levels off or flattens out and becomes stationary, and then it continues in the same way. We call this a point of inflection. So you spell that this way, where the curve just kind of inflects on itself, but it doesn't actually change its direction in terms of its gradient. So it's an inflection. Sorry, there's no S. I'll just scribble that out because I'm not very good at erasing using this. So it's a point of inflection, and the y value, look, when x equals 2, the y value is just 1. Right, here we've got a trig equation. And the important identity to remember here is that tan of x is equal to sine of x over cos of x. Really, really important one. You'll see why in a minute, but you do need to learn your trig identities for sure. So if I, from each side, just subtract 5 sin x from both sides, I'm going to be left with 8 cos x is equal to -5 sine of x. If I then divide through by cos of x, I'm just left with 8 is equal to -5 sin x over cos x, which is effectively 8 being equal to -5 tan x. Then if I divide through by -5, I've got -8/5 being equal to tan of x. So I do tan to the -1 of -8/5, so x is equal to tan to the -1 of -8/5. And that gives me, hold on, you can just check that your calculator's in the right mode here as well. It gives me -57.99, and I call that -58. I think it's sufficiently accurate. Now, it does want it between 90 and 180, so I've just got to consider my tan graph for a second. So my tan graph looks a little bit like this. It's positive in the first quadrant, and that's 90, 180, 270, and 360. I only need to go up to 180, don't I? So I'm not that interested in that. And then it comes in negative here. So it's this negative that I'm interested in. If you think about it, what it's given me is the answer that lies back here. So it's given me this answer here of -58, but that would also exist here, wouldn't it? Which would be 58 back from 180. So 180, take away 58, gives me 122 degrees. Another one of your trig identities you need to remember is that sin or sine squared x add cos squared x always equals 1. So here, the only difference between the left-hand side of the identity and the right-hand side of the identity is that there is no sin of x. So it would be quite nice to kind of sub that out for cos. So if you think of rearranging this, you've actually got 6 lots of 1 take away cos squared x plus 4 cos squared x. If we multiply that out, we have 6 minus 6 cos squared x plus 4 cos squared x. We're starting to look a little bit more like the right-hand side of the identity. So we've got a constant here, -6 or -6 cos squareds, add 4 positive cos squareds would be -2 cos squared x. So A is 6 and B is -2. This question, there's a lot of information on the page. There's also quite a lot of marks, but again, I would just encourage you to get going, have a go, see what happens. So it says for each of these two function machines, when the input is A, the output is B. So we're going to have two different expressions for B, and then hopefully we'll be able to put those equal to each other to eliminate B and get something that just has A and K in it. And then it wants us to work out an expression for A in terms of K. So we'll have a little play about. First off, I'm saying over this side that B is equal to A squared, add 3, and then all of that is multiplied by K. So I'm going to call it like that. Next up, on the bottom one, B is equal to AK, all squared. That whole thing is squared. And then we add 3. Right, that's a little bit more complicated, so I might just neaten that up a bit. It's actually A squared, K squared. I don't want to forget any of that, and I'm adding 3. Next up, I'm going to put them equal to each other. So I've got K lots of A squared plus 3 is equal to A squared, K squared plus 3. because I've just put the two b's equal to each other. I want a in terms of k, so somehow need to isolate a here. Let's have a little look. If I expand this bracket out first, get ka squared plus 3k equals a squared k squared plus 3. So it'd be really nice to get the a's all on one side, ideally, if that's possible. So, no, cancel that. Do you know what? And I'm kind of glad I've shown this. I'm going to go back a step and I'm going to divide through by k because I think it might make things a little bit easier. That'll leave me with a squared plus 3 is equal to, so sorry, I'm dividing all of that by k and everything there by k. So that will leave me with a squared k plus 3 over k, because that needs dividing by k as well. Next up, what could I do? I'm going to take away 3. In fact, no, do one thing at a time. So I'm going to take away 3 over here. That leaves me with a squared is equal to a squared k, add 3 over k, take 3. I'm going to take away the a squared k on this side now. A squared, take away a squared k equals 3 over k, take 3, and I'm going to come up here now to continue my working out, if that's alright. So I'm going to take a factor of a squared out because I'm getting a bit closer to isolating a on its own. So what would that leave me with? Leave me with 1 minus k, which is equal to, I'm also going to make this fraction a little bit better. So I'm going to make them both things have a denominator of k. So I'm going to keep 3 over k, but I'm going to make that 3k over k, because I think that might make things a little bit easier in a minute. Then what does that leave me with? If I want to divide through by the factor or the bracket, it leaves me with 3, it leaves me with a squared is equal to 3 minus 3k over k, all divided by or times by the reciprocal times by 1 over 1 minus k. And the reason I think that's quite useful is because if you think about this numerator of the first fraction, it factorizes. So a squared is actually equal to 3 lots of 1 minus k all over k times by 1 over 1 minus k. Now they're going to cancel off top and bottom. That means a squared is just equal to 3 over k, and a therefore is equal to the square root of 3 over k. But it's all just a matter of mucking about with it and seeing where it leads you. You can see over here, I didn't like where that was going, so I kind of readjusted. Here, I think this step is conceptually quite difficult. I am dividing by 1 over k, but that's the same as multiplying by the reciprocal of it, so putting 1 over it, if you like. I hope that all makes sense. Now, this question, I think, could actually be on the GCSE higher paper. The numbers work out alright in the end, I'm hoping, but it's only a little bit tougher than a GCSE question. Here, we're asked to work out the value of p. Well, p is involved as a power on all of these. So I'll start looking at the numbers that are being raised to the power, 9, 81 and 27, and what I notice is they could all be written as powers of 3, because 3 squared is equal to 9, 3 cubed is equal to 27, and 3 to the power of 4 is equal to 81. So I can get all of these in terms of 3 and then think about how the powers interact with each other. So first off, I've got 3 squared all to the power of 0.5p. I'm multiplying that by 3 to the power of 4, and that equals 3 to the power of 3 all to the power of 2p minus 1. So all I've done is kind of substitute these powers in place of 9, 27 and 81. Now let's have a look. Remember that when you've got a bracket with powers, you multiply. So that would be 3 to the power of, or 2 times 0.5 is just 1p. And I'm timesing by, well, there's nothing to sort out there, it's just 3 to the power of 4. But there is another bracket to expand here, so that would be 3 to the power of. This is all multiplied by this, so it would be to the power of 6p. Take 3, because the negative one needs multiplying by 3 as well. Okay, the rule of indices when we're multiplying is that we add. So here I've effectively got 3 to the power of p, add 4, and that is exactly the same as 3 to the power of 6p minus 3. Now because I've got the same number raised to different powers, but I've got an equal sign in between, it ultimately means that p plus 4 is equal to 6p minus 3. It's the only way I would get the same thing if I raise the same number to those powers. So I've got a simple linear equation. I'm going to take away p first, so I've got positive 4 is equal to 5p, take 3. I'm going to add the 3, so I've got 7, or positive 7 if you like, is equal to 5p. And so p is just equal to 7 over 5, or 1.4. That's it, we're done. Sorry, that's been an absolute epic from me. Lots of words, lots of things to look back at, in particular that question on matrices. Okay.